So my name is Elmir. I'll be talking about the separation optimization by chemical application in oil and gas production. I'm a production chemist working in oil and gas production operations in BP, Azerbaijan. I complete my degree in chemistry. Right now I'm completing my Master of Engineering in Chemical Engineering department. So just wondering how many of you are from chemistry or chemical engineering background? Just raise your hands. So, too many. So you may find it interesting, and I try to keep it as understandable to everyone else. I try to keep it very interesting to everyone. So the summary is that I will start with process overview of oil and gas production, how we produce, and general overview, and then I will move to chemical aspects of produced fluids, how chemistry is related to this production, and then I will move to chemicals we use to optimize separation operations which are done in oil and gas. And these chemicals are demulsifiers mainly, antifoams that we use, and then I will talk about waterclarifiers, and I will then move to performance monitoring, how we monitor the performance of these applications, and at the end I'll move to question and answers. But if you have any question, you can stop me anywhere and just ask your question. First of all, this is the This is the general overview of production process, basically offshore platform and where we produce oil and gas. So fluids coming from the wells, production reservoirs, through the production manifolds to multi-stage separation system. We usually have multi-stage separators. The first one is usually a high pressure separator. The second one is usually the low pressure separator, and where we have gas, water, and oil separated from each other. Depending on the process parameters, we may have some heat exchangers somewhere in the system. And we also have test manifolds, test separator. We use this part of the process to test the fluids, their new wells or some new applications to understand their future behavior. So this is mainly it. And in the next slide, I summarize the chemical injections, how we do the chemical applications in this system. So mainly the chemicals we use to optimize the separations are mainly demulsifiers, antifoams, and waterclarifiers. So demulsifiers are mainly injected to the separator inlet. Antifoams are also injected where we expect a foaming. Before that location, we need to have some antifoam in place to avoid foaming issues in the system. And we also have waterclarifier to purify the water coming out of the separator to the oil, to separate all the oil from that water. So this is the purpose of why waterclarifiers are applied offshore. So mainly this system placed in an offshore platform. So the purpose of this system is to separate oil from gas and water, to send oil as much clean as we can to the terminal, which is located on different areas. So the purpose is to have around 5% of water in the oil product, which can be as high as 80% from here, and 5% is the target of the oil product that we produce. So first of all, demulsifiers. They are also called emulsion breakers. So emulsions are the undissolved particles that's dissolved into immiscible solutions. So we use this kind of chemicals to demulsify the system. So these applications help us maintain 5 water or even lower water content in the system. And they're usually injected upstream of the separation vessel. Where we have separation vessels, before that vessel, we need to inject this chemical to get efficiency of it as much as we can. And imagine this is a separation vessel. So I summarized the demulsification in 4 steps. First of all, these are little droplets of water in the system. And these are total oil. So we need this water all completely separated from the system because it doesn't make any money. So we need oil because it brings us energy. We use it for different applications, but water needs to be separated from this system. So first of all, we have water droplets in this system. Imagine this is a separator. And when we apply this demulsifier or emulsion breaker to the system, these molecules come and find these water droplets, and because they are surface active chemicals, they change the surface activity of these water molecules, and they become more attractive to each other, and in the third part, they coalesce. So they get closer to each other. When they are big enough to settle out, they just settle down here, which is easier to separate, to get the water out. We need long enough contact time of the chemical to system to have this efficient separation. And this settlement of these water molecules can be explained by Stokes' law of settlement, so which says that the velocity of the droplet down the system depends on the droplet size, the density difference of the droplet and of the system fluid, gravitational force, and viscosity. Which means also if we increase the heat, so it will reduce the viscosity and we will get good separation. And also if the droplet sizes are bigger, it's easier to separate because it's in this part and these are directly proportional to this. So these demulsifiers help us to increase this velocity of the droplets to get them down and separate them from the system. So emulsion breakers or demulsifiers, they're mostly non-ionic polymeric chemicals, but we may also have some kind of charged chemicals, polymeric, anionic or cationic. Their molecular weights are about 2,000 and 50,000, and their injection rate up to 30 ppm. This is the injection rate we usually apply. So for example, if the production rate of oil is 100,000 barrels a day, we need to inject 20 liters an hour of this chemical to treat the system and to get good separation efficiency. They can be injected anywhere downhole in the reservoir or in the wellheads where the reservoir fluids come up the surface or in the separators. And some demulsifiers are better than others. So you may always find a better product than your product, than the one you are currently using. So you need continuous improvement of your chemistry and of your system to see how you can optimize your separation. And it's also important to note that all emulsions can be treated. So some emulsions are very hard to treat. Some waters cannot be separated at all. But a good demulsifier can help us do that. So some product examples. The most commonly used application of demulsifier, this is the chemistry, alkyl phenol, aldehyde ricin alkoxylate. So it's basically the alkyl phenol aldehyde. Alkyl phenols are condensed with aldehyde and then ethoxylated with ethylene oxide and propylene oxide to get this product. And this is another type of polymer that can be used as demulsifier. It's formed from 2,6-toluene diisocyanate, and it's a polyethylene polyacrylate. So these two chemicals can be used together. So in some part of the world, they use this chemical together, and they get better separation efficiency. And some people try to use only one. Some people try to get different formulations depending on their process and depending on their chemistry of the fluids. So I try to show how the demulsifiers behave in the system. So this is actually a three-phase horizontal separator where we have oil, water, and gas coming into the separator here. We have three-phase here, and sands or solids are going down right here, and we have water and oil here. Above this weir, the oil flows to the oil outlet where we need to have 5% or less water content. And gas are moving up to the system where we extract or get the water from this lake. So this is I put actually a video. I'm trying to open it. I just tried to show how the emulsifier work in the system. They separate oil from water, but okay. So what we need is to have this. This is real oil sample from the well or from the separator with emulsified water. When we apply the emulsifier, they get separated. And this is what we need to happen right here to get better oil product. So this is all about the emulsifiers. And so the emulsifier applied to this bottle, which is mainly composed of oil and water. Now, and after some time, so you can see the difference. I'll move to the antifoams, so the video didn't work well. So antifoams are kind of chemicals that we use to optimize the separation efficiency in the system. So this is what foam is, actually. When you pour acidified, pressurized fluid or drink to the glass, and if you are not very careful, you may get this. This is something we don't want to have in our process, because in three-phase separator, the foam can cause too many problems. First of all, I need to note that the poor liquids do not foam. If you have only water, it doesn't foam. You need to have some surface active components in that to have foaming, and it's caused by surface activity. And no foam is stable forever. No matter how foamy your liquid is, if you leave it for few hours, it will go. The foam will collapse. But unfortunately, we don't have that long duration in our system. We only have few seconds to collapse this foam, which is why we need antifoams, antifoam chemical. So what's wrong with foam is that as I said, the poor level control in the vessel is the first foaming concern in the system. And also when there's a foaming, we may have some carryover of liquid to the gas outlet of the separators, which may have downstream problems. And compressor trips are one of them, which needs to be avoided. And gas also carry over to this oil outlet where it shouldn't, where we shouldn't have gas in the oil outlet. We should separate water, oil, and gas separately as much as we can.
Eldar Mansimov, Caspian Drilling Company, co-work operation, well drilling operator. Just you said, thank you first of all for great presentation, Mr. Elmir. My question is you just spoke about the advantage of this presentation of the default.
Antifoams.
Yes. And what's the disadvantages of? Because being a disadvantage, as I know, it's sensitive to the minerals, and also it should change at the pH changes. And how you control such kind of situations?
Yeah, the good question actually. But when you introduce a new chemical to the system, so you have to be aware of the risks you are bringing to the system. You have to be aware of its chemical behavior in the system and its compatibility with system fluids, with the system material, and the other chemicals you are injecting, and even the downstream process facilities. For example, if I'm using a chemical in an offshore platform, I may have some problems happening in somewhere in a different country where they use that crude oil for producing different products. So that's why when you introduce new chemical, you already have your information, what you should expect, and you have to decide, do you take that risk or that risk? So you have to understand the difference of that risk. You have to accept one of them. If the second risk is not acceptable, you just don't introduce and stay. Yes. Whichever benefits you more, you can take that one as an advantage and take the risk of the other. Did I answer your question?
Yeah, of course, thank you.
So yeah, antifoams or defoamers, how they work. So imagine this is a crude oil film between two gas bubbles. So these are gas bubbles and these are crude oil. And when I inject antifoam to this system, it spreads at the interface and breaks the film of oil so that we do not have any oil going up, any foaming issue. So this is basically the general principle of antifoams and how they work. And their application is basically done upstream of the foaming concerns, where you expect your foaming to happen. In the separator, so you have to inject before the separator. If that happens in some kind of flash tank, you have to be injecting your chemical upstream before your fluid goes to the flash tank. That's the injection location of the antifoams. And typical injection rates are 1 to 15 ppm. You may have efficiency at 1 ppm, or even you may have to increase your dose rate to 15 or 10 to get good foam collapse. But increasing the chemical rate is not always a solution. So when you overdose your chemical, you have to be very careful because it may have some reverse effects. You may have some, while you're solving a problem, you may have your worst problems in the system. That's why you have to be very careful in measuring the chemical injection rates in your system. And commonly used antifoams are silicones usually. This is one example, the PDMS, polydimethyl siloxane, and glycol-based antifoams are also used in glycol system. We can also use this in crude oil system by formulating some kind of polar solvent, non-polar solvents. So lastly, water clarifiers. So when we separate water, unfortunately, it's not 100% water. We have some residual oil in that. So while I was talking about water and oil emulsion, so this is oil and blue droplets are water. The reverse emulsion is that when you have water, the main phase, and oil droplets here. So this is a concern. This is a water quality issue because it's a serious environmental concern for offshore operations. If you produce water from the system and you separate that water, you use an offshore platform, you have to keep it as clean as possible because it contains oil. If it's discharged to the sea or any marine environment, so you contaminate that system. That's why you have to be able to clean your water as much as you can. And target is usually below 30 milligram per liter. For each liter of produced water, you have to have less than 30 milligrams of oil. So this is a very strict target, and it's a very big challenge to reach this target, to keep your oil concentration below this. And this oil droplets also damage the process equipment. So you don't want this because it may plug your pumps, filters, or injection equipment. And I put a typical offshore produced water system in North Sea. While we have water separation in this part of the systems, this is a multi-stage separation system where we have water separated here and oil separated here, which is sent for further treatment. But waters from each separator are separated and treated by mechanical treatment units, which are usually hydrocyclone, flotation vessel, or degasser. We need some kind of chemical to help these mechanical units separate oil better. So this chemical are called water clarifier. They clarify water. This is the general name. It has some kind of different chemistries, up to hundreds or thousands. So how they work? So first of all, this is the dispersion of oil droplets. So it's like dishwasher in your kitchen. So if you pour some kind of oil to your water, and you have this picture, unfortunately. And some of these oil droplets are charged, plus or minus. When you apply water clarifier to this solution, they unbalance their charge. For example, plus charges become 0, and negative charges on the droplets, they become 0 again, and so they become more attractive to each other, and they start coagulating. They get together and get bigger and bigger, and this is the oil coagulated by the droplets here with the help of the chemical we apply. And at the end, they separate, the oil forms a separate layer and goes up because of density. So typical dosage is 5 to 20 ppm, parts per million. And there are two types of water clarifiers. General classes are flocculants and coagulants. The flocculants are usually polymers, and they induce the settling particles and grow into larger flakes, like this. So this is actually a physical process. So the type of chemical, I just put an example here. This is a DADM AEC polymer. We actually don't care about the chemical formulation, the chemical composition of this flocculant, because it's a physical process. You only need to coagulate floc to make bigger floc to make your separation efficient. So that's why if the polymer is okay, you have to apply that chemical, that system, and get your separation along with the coagulants. Coagulants are water-soluble water clarifiers, and what their function is, what they do is they, as I told in the second step, they imbalance the charges of oil droplets so that they become attractive to each other. So they get close to each other, and while they were minus and plus, they are not attractive. They do not attract, they repel each other, but when they are recharged, they are becoming neutralized and start liking each other. So they get together. So this is the function of the coagulant, how they work. About these three chemicals, the three type of chemicals, and how we monitor their performance. How do we know that these chemicals work? So basically, for each chemical application, we need to have monitoring parameter and usual targets for it. I'm injecting this chemical. So why am I injecting this chemical? Because I need to lower my water content in the oil product. I need to have at least 5% of water in oil. That's why I need to monitor the water content of crude oil product. I take sample, go to the field, take samples, and look for the water composition, water content, and I say it's 3%, okay, that's fine, so we are good. So usual target is -5, less than 5, sorry. So the chemical application, the number 2, Antifoam, and monitoring parameter is liquid carryover to the gas outlet. We keep records of the gas analysis, that we also look for the liquids in that gas, so make sure that we are not foaming in the system. And it needs to be below the process specific limit, which is defined by the project team when they design the system. And it also affect the, as I said in the previous slide, the level control. That's why we need to monitor the level control. We need to be very careful when we control the level, because we don't want any high alarm due to foaming. So you have to be very sure that you are not foaming the system and your chemical application is in place, and you keep dosing your chemical to avoid foaming in the separator. And water clarifiers are monitored, their performance are monitored by oil concentration in the produced water. We analyze water samples for oil concentration, and we try to stay below 30 milligram per liter. If we are above this target, we have to do something. We have to think something differently to keep our concentration below 30 milligram per liter. So all in all, the summary is good oil water gas separation requires good chemical treatments. If your chemical treatments are good, so you will get your separation efficient as long as your mechanical separation is also working well. But overdosing is not always a solution. While you try to solve a problem, make sure that you are not creating something worse. You are not causing something worse. That's why you have to be aware of all the risks that our friend just asked a question about. And you also have to monitor your system continuously to make sure that you are treating the system as you should. And last thing, I would say that there's always a better product and an opportunity for optimization. If your demulsifier or water clarifier or Antifoam are working well, so it doesn't mean it's the best product. You can always find a different product which can work at different dose rates, lower dose rates, or you can optimize your current chemical treatment. If you're, for example, injecting 20 liters a day, why not to inject 10 liters a day? Did you check it? So you can just optimize your system by playing on the chemical injection rates and doing analysis from the system and get your most efficient process conditions and keep operating as safe as you can. That was all, actually. I hope you enjoy it. Any questions?
Hi, I'm Abbasoghlu. Thanks for giving a lot of information about this valuable topic. I have a question about the first stage separation process. Can we separate gas from oil, water, I don't know, sand mixing by some chemical? For example, monoethylene glycol and other chemical.
You can, first of all, the separation by chemicals are done when there's the concentrations are very low. For example, you can, if you try to get 0.1% of some contamination you have, you can use chemical. But generally, what we use for separation is for mechanical units like separators or flush tanks or distillation towers or cooling towers. Chemical treatments are secondary barriers that we apply to improve these mechanical treatment units, actually. But purely just applying the chemical to the system, it would be very expensive because you can do it by mechanical operations. Why to invest too much on your chemical application? So chemicals are helping that mechanical because mechanical separation units are cost efficient, but when at some degree it's not 100% efficient, so it needs some help from the chemicals. That's what we do, actually.
Thanks.
Did I answer your question?
Hello, hi. Can I ask you a question, by the way?
Yes.
Actually, it's a very great presentation. We know that the emulsifier is a very good solution, by the way. I mean, that's why it has been used by industry for years and years. But my question, or maybe just to get you some opinion, if we put something like chemical, the emulsifier, will that be affecting the quality of the crude itself?
Emulsifiers?
Yes, and my second question will be then, crude and water, in order for them to be emulsified, they need energy. This energy comes from the flow. Can we, for example, design a system in the production, maybe in terms of the pipeline and so on, that we can actually reduce this energy so that there's a less emulsion problem, rather than treating with some chemical?
Yeah. The answer to your first question, using emulsifier, not demulsifier, is actually a practice done in oil and gas operations. It's when the wells are not flowing well, for example, if the pressure is very low, bottom hole or down hole, we introduce some kind of emulsifying chemicals. It brings some foam. It energizes the system to keep the well flowing. So this is where we apply emulsifier. But when it comes to the surface, so it needs to be demulsified because we need to separate the water from it. That's where we apply demulsifier. So this is the answer to your first question. So emulsifiers are applied, actually. The second question is, yes, we need to reduce the energy of the system. That's why in the presentation, if you remember, I put multi-stage separation. The first one is high pressure. The second one is low pressure. And to get a good separation at the end, your end point have to be atmospheric or even below atmospheric pressure. So we usually have HPLP separators on the offshore platform, which operates at 10, 15, or 20 bar, and it's pumped through the subsea pipeline to the terminals where we have atmospheric separation. At the end, we neutralize the energy we are having from the wells just to have good separation, and at the outlet of the oil and gas terminal, which is located onshore, is 0.3 or 0.2% of water. So yes, we reduce the energy and we get good separation by doing so. Good.